completely, well, almost completely different. That's the new title, by the way, of Alan's talk.
Yeah, well, thanks for coming back. And I hope you'll indulge me that instead of telling you the story of the wonderful opportunities of wave turbulence, and really that's a very exciting area, and it's a sort of story far from over in the sense that it's not a completely solved problem at all. And but I've been playing with some other ideas recently, and when I came here and I saw this beautiful virgin blackboard, and then I saw that on Friday John Bush and Yves Couder were going to entertain you with some science fantasy. I thought I'd get it in a little bit ahead of them with a bit of fantasy of my own. So what I'm going to tell you about is objects that arise in pattern-forming systems. Now, the granddaddy of pattern-forming systems is Rayleigh-Bénard convection, a fluid heated from below. And at first, of course, if you have a horizontal layer of fluid, the heat is carried across the layer by conduction. But once a critical temperature difference is reached, then the fluid decides that the heat gets carried from the bottom to the top by convective cells. And the first thing you learn is that there is a preferred size of these cells. For instance, if you had a fat cell like that, okay, the friction that the parcel of warm fluid would feel going along the boundary for so long would not be enough to, it would be too much and would overcome the buoyancy. And so you wouldn't get any motion. You might think, well, why doesn't it just do it nice up and down, nice thin cell? That sounds a very good idea. The trouble with that is if you have a very thin cell, the rising warm parcel is too close to the descending cool parcel, and by conduction, you see the rising parcel loses its heat and therefore its buoyancy, so the motion actually comes to a stop. So there's a sort of preferred wavelength. There's a preferred wavelength. Now, in a system where this wavelength is small compared to the size, the horizontal size of the system, we call those large aspect ratio systems, and where I have both translational and rotational symmetry in the original geometry, okay, then, of course, what will happen is these cells of this size, but with different orientations, will start competing with each other, okay, as they start to grow up. And a winner, out of this competition, a winner or winners will emerge. Now, for today, I'm going to imagine that rows or stripes as the winning configuration. Okay? But then again, the orientational degeneracy has something to say, because, you know, in natural convection in a big box, the patches will orient themselves according to local biases. And so, in fact, a natural pattern tends to consist of patches of almost parallel rows or stripes, okay, mediated by defects of both line and point defects. And it's these line and point defects, particularly the point defects, that I want to tell you a little bit about today. They have some very interesting properties. All right, and now there's a competition with a prize. This is an elliptical basin. It's got a little lopsided on the right, but that's because I'm not a very good drawer. And now so this is the cross section. You're looking down from above. It's a shallow basin, elliptical basin, and we're heating from below. And I'll also heat the sides. Now, because I've heated the sides, you know, the fluid, you imagine the fluid will rise here along the side boundary, and then will descend here in roll-like fashion like that. So the next rising thing will be something like this. And your job, before I get to the answer, is to fill in the rest of the ellipse. Okay? And there's a prize. And the prize is a bottle of whiskey, which which will go to the person who gets closest to the answer. So this is we're going to take this fairly simple geometry and learn some very interesting features. Okay, well now, a little bit of theory, a little bit of background. First of all, because I have roll solutions, the field of rolls, now we're far from onset, okay? We're at Rayleigh numbers, or critical Rayleigh numbers. We're at Rayleigh numbers far above the critical. So essentially, the amplitudes tend to get slaved to the wave number and the whatever stress parameter you have, like the Rayleigh number. So you get these exact solutions, 2 pi periodic solutions. So this represents these 2 pi periodic solutions, which are just rolls. Now, to calculate them, you can just expand things in a Fourier series and compute the coefficients. And you'll find, to leading order, you'll get all the amplitudes will get slaved together, and the first amplitude here will get slaved to some function of k, the modulus of the wave vector k. The k is, if we have a rolls like this, k represents, we call that the wave vector. Its size is 2 pi over the local wavelength, and its direction is normal to the lines of contours of constant phase. And so now we're going to ask ourselves, okay, but we're not really, most natural patterns, the wave number isn't a pure constant, but varies slowly over the box, at least in most places. Near defects, of course, it'll change quite suddenly. And so we're going to ask, is it possible that nearby this exact solution, there is a slowly modulated solution? Okay? So I'm going to introduce now my phase will be, say, the integral of k dx. Okay? Big X here is epsilon times little x, where epsilon, the small parameter in this problem, is not distance from critical, but rather the inverse aspect ratio. Now, because this is no longer an exact solution, okay, there'll be terms left over which take account of the fact that this k and the theta depend slowly on the space and time variables. This is no longer an exact solution. We have to look for corrections. But now, this original system, say the Overbeck-Boussinesq equations, because this guy has a translational symmetry, the equations linearized about this solution, okay, will have non-trivial solutions. Okay, the homogeneous equations linearized about will have non-trivial solutions, which essentially, in other words, df by d theta will be, because if I can shift x by a little bit, essentially df by d theta will solve the linearized PDEs around the initial state. And because of that, there will be constraints. In order to solve for the corrections, there will be various constraints. The phase and the wave vector can't just change in any old way. It has to change in a very well prescribed way. And this is the way it changes. All right? You get this lovely nonlinear diffusion equation, where this guy is a quasi-linear operator here. You can see k is gradient of theta. So if I write this out in coordinates, I would find something times d2 theta by dx squared, plus something times d2 theta by dx dy, plus something times d2 theta by dy squared. So this tells you that the phase it will diffuse due to the fact that the wave vector isn't quite constant everywhere. Now let's take a look at this, because this is very important. This is universal. If I drew you the KB for a model like Swift-Hohenberg or for the Overbeck-Boussinesq equations, by the way, I'm working at high Prandtl numbers, so I'm no soft modes. I'm not allowing kind of overall mean creep or mean flow modes here. So high Prandtl number for those who know about such things. So I'm going to take a look at this guy. And this guy, his graph is sort of universal versus K. It starts at the edge of the linear stability boundary of the original problem, and it looks like this. Okay? It has this kind of cubic shape. And it's absolutely, like I say, universal. The actual, the details, of course, depend. I'm looking for some yellow chalk here, but there we are. The details, of course, depend upon the problem, but the basic shape doesn't. Now, if I look at this quasi-linear operator and I diagonalize it, I find the eigenvalues are. So this is the graph of KB. And if I find that the eigenvalues are B and the derivative with respect to K of K times B. Now, if I look at this graph, then you see this guy is positive here. This guy is negative. Okay. Here, both of them are negative, and that's good, because if both of them are negative, then this is a good diffusion equation. Okay, it'll be b times d2 theta by dy squared plus d by dk of kb times d2 theta by dx squared. Okay, so actually this is the stable region here, and this is often called the Busa balloon. Okay, but regular patterns very seldom live in the Busa balloon. They tend to live. There's a preferred wave number, which is this guy here. Okay, but they tend to live just to this side, on the unstable side of that. So this would be d theta by dt is minus b d2 theta by dy squared, but if b is positive, that's reverse diffusion. So this is ill-posed, okay? Ill-posed. And what happens is if you have a roll slightly too big like that, what it likes to do is get a bend in it. Like that. So this goes back to being the preferred wavelength, and then you get this little bend here which reflects the original size. So so basically in a pattern, if you looked at the statistics of wavelengths or wave numbers, you would find roughly that there's a huge most of the power spectrum would sit just to the left of the preferred wave number. Okay. So now to deal with this, of course, this then is kind of hyperbolic or a bad diffusion. So I have to go to the next order, and I have to add a little bit of regularization. So you have to actually calculate this, and this is calculable. And what you find then is this extra term, which regularizes things. And now I find I can express this as a free energy. Okay? So this will be d theta by dt. And this free energy has the following form. Free energy has the form of, you can express it in terms of a functional of b, but what we're going to do is approximate things by looking just in this neighborhood here. And so it's actually just 1 minus k squared all squared, or 1 minus gradient theta all squared dx, and plus then the free energy giving rise to this guy is del squared theta all squared. So now I know fluids, even high Prandtl number fluids, aren't exactly gradient flows. But at high Prandtl numbers, actually, the patterns of Overbeck-Boussinesq patterns actually behave as if they're gradient flows. So, and this is remarkably familiar, because you see, this is if you know a little bit about stretching of sheets, if you have thin elastic sheets, this is nothing other than the stretching term. If I, for instance, take an elliptical cross-section like this, and I heat it so that the sheet comes off, the blister comes off the substrate, okay, its increased area, say A, and the original area projection is A0, so there's a natural wavelength, or there's a natural slope in this case. So theta is just this height of this blister off the xy plane, okay? So this guy, the square here, this guy tells you how much stretching has gone on. It tells you the difference between the actual slope and some preferred slope. The preferred slope being gotten by taking the ratio of the area of the blister off the plane to the projected area. Okay, so you pay a price if the gradient of the slope isn't quite right. And you also pay a price, and sure, you recognize that. That's just the curvature. In fact, this is the mean curvature squared. And for those who do a little elasticity, in fact, this is just the mean curvature squared minus a quarter times the Gaussian curvature. The Gaussian curvature, as you may know, just integrates out, okay, to a boundary term, okay? So the variational problem is can be cast like this without it. Now, here's a remarkable fact. So now we're thinking thin blister, okay? So now we're imagining that this is a blister, this is on the ground, and now this has come off the plane, and these are constant height contours, okay? They're constant height contours now, okay? So here's a wonderful thing, magic thing. If I look for solutions by balancing, look for self-dual solutions of this free energy by balancing the bending energy with the stretching energy, okay, then those solutions are solutions of the full Euler equation for the full thing, which would be a fourth order equation, okay? In other words, this equation, the right-hand side of this equals 0, okay? Solutions, self-dual solutions, are solutions of the full problem if the Gaussian curvature of the self-dual solutions is 0. But for most developable surfaces, that's the truth, you see? And even at corners, even on edges, okay? I mean, if you have an edge like this, an edge like this, like that, top hat, the Gaussian curvature here, even at the bend, this sharp bend, is 0, because there's curvature certainly in this direction, but no curvature in this direction. So these self-dual solutions are very valuable. Actually, we don't really need to say that the solution, because this is a non-convex problem, variational problem, so we don't have uniqueness, or we don't know what the solution is, but we can trap its energy. And so what I'm going to actually tell you, I'm going to tell you what the solution is here, and I'll tell you, I can't say that that solution is unique, but I'll tell you that that solution's energy is the energy that will be achieved by the system. Okay? Now, this is lovely because actually if you take the self-dual solution, it means del squared theta is 1 minus del theta all squared plus or minus. So let theta equal epsilon log psi, and you get the Helmholtz equation. So it's like a Hofkohl transformation. So you can solve these shapes, for instance, straight parallel rows like this are solutions when you take this new phase or height function. I've said theta is epsilon log of psi. When you take this psi just to be e to the kx. If you take it the sum of two, e to the k1x and e to the k2x, you describe this. So you have a boundary layer here, and so on like that. Okay? So it describes these line defects. We call them phase grain boundaries that occur in most of these systems. Actually, you know, if you just look at patterns in you know, ferrofluids or fluid, I mean, in a whole variety of situations, you'll see patches of straight rows mediated by these line and, in a minute, point defects. Now, what's the cost of this? Well, you can work out the cost. It actually, if this angle here is alpha, okay, that angle there is alpha. The cost per unit length here goes like the cube of alpha. So it's the length of the grain boundary times sine cubed alpha. Okay, it's very easy to calculate that just from the solutions I described. Now, so actually, the solution here is the following. The solution is I take the so-called iconal solution. In other words, I come in along this normal, and I put the new phase, or the new height, exactly at the preferred wavelength along this line. So I do this at all these points, and of course, that sort of solution, you'll get caustics, okay? And the caustics will look something like that. There's one focus, there's the other focus, and the caustics will be something like that. Okay, so you get multi-valued regions, but we all know how to resolve the multi-valued regions. You just put a shock in here, or a phase grain boundary. So the solution for the thin blister problem is something like this, and these contours go around like that, and so on. But inside, there's this discontinuity in the K vector that changes over boundary layer thickness right here. Okay, so that's the thin blister problem. And you can show, we've shown that you can trap the energy of this system on the upper bound. You can use the self-dual solutions. On the lower bound, you can use a trick shown to us by Bob Cohn. And so you know that the actual solution will have the same energy as this one that I've drawn. Now, the experiments on fluids for convection don't show this. They sort of show it. It's very close, but not quite. Now, what's wrong? You see, there's a huge difference between the elastic sheet problem and the pattern problem. What's the difference? Supposing I have here in the elastic sheet, I have a bend like that. So I take a page and I just bend it over a crease. Now that costs. That's a real cost. Okay? The gradient of h in this direction is like this, and the gradient of h in this direction is like that. So that's a real cost. But in the convection problem, there's no cost. Because, look, it's all a matter of labeling. So if you take like the limit of these things, if this alpha gets very, very large, okay, so the alpha gets up towards pi by 2, so the bend here, you know, so it's like this, they're almost parallel, then it's really just a matter of labeling, right? Because, you know, this is 0, this is minus 2 pi, and this is minus 2 pi. I mean, there's no cost to that in a convection pattern, okay? The fact that the gradient of theta is discontinuous across this line is purely an artifact, and what it tells us is something very important. It tells us that the gradient of theta for patterns is not a vector field, okay? It's a director field, okay? In other words, it's a vector field without an arrow. Okay, so you see this for alpha getting very, very towards pi by 2. In other words, very sharp bends like this. What I'm telling you is in the pattern that costs nothing, but that's maximum cost for the for the elastic sheet. So now what's going on here? Well, obviously the sine cubed alpha, this cost in the convection pattern, the solution, this solution, has got to have something wrong with it as you get sharper and sharper bends. And what's wrong with it? What's wrong with it is this, okay? If you take bends like this, okay? Now, let's imagine we're going to extend it here, okay? So this is my alpha now. So this is my alpha, okay? So this distance costs me L sine cubed alpha, where L is the length of that guy. But you see, I can do something better. I'll take the bisector of that angle. I'll put in another phase grain boundary there, and another one on the other side. Okay? Now the alpha, the angle between the wave vector and the phase grain boundary, this guy is pi over 4 minus alpha over 2. Okay? But of course he's much longer, and there's two of them. So the cost is 2 times sine cubed pi by 4 minus alpha over 2 divided by cos pi by 4 plus alpha over 2. That's this angle here, taking the projection down like that. Is that okay? So what I'm doing is I'm going to replace this guy, where the bend goes like that, with this guy, and put in things like this. Okay? So I have a nipple, okay, popped out. All right? So I claim the cost of this bit is log small. It's not very big. The cost of this you can work out. It's this. And this is just 1 minus sine alpha. Okay? So when alpha gets big enough so that the sine cubed alpha becomes more than 1 minus sine alpha, which happens at about 43 degrees, you get these nipple instabilities. So, for instance, if I had a saddle pattern, the saddle pattern would look something like this, okay, where the phase grain boundaries are at 45 degrees, I would see the saddle pull apart into two things like this. Now, what are these guys? These guys are very interesting. Okay? This is what we call a concave destination. These are the point defects that I want to tell you about. Okay, I'll draw it now big. Okay, so it's like this. So you have phase grain boundaries here, here, and here. And so this is what the structure looks like. Okay, and the stable one is when you have a 120 degree angle here between these guys. So roughly his cost goes like L and then sine cubed 60 with 3 of them. Okay? So this is called V, a convex declination. Okay, so declinations are well known to people who work in liquid crystals, and we see such things. On the other hand, we also have a convex declination, which looks like this. Looks like a loop. It's like half a circle, half a target pattern. Okay? And we call these X's. Okay? So, what I'm telling you is there is a natural in natural patterns, because of orientational degeneracy, when the different patches of constant rows, stripes, get together, they're mediated by these lines and point. At the end of the lines are these point defects, concave and convex declinations. Now, if you want to see them, just look at the tips of your fingers. Okay? You all have, they're called triradii, is the concave declination. You'll see one with this topology, okay? Usually where the ridges down on this crease come in this direction. From here they're coming in this direction, and here they come like that. So you'll see lots of, usually 1 or 2 triradii or concave declinations on each finger. You'll also see you'll either have perfect whorls, but most of us have just loops near the center. Okay? So these are topological objects, very interesting objects, because look, they have an interesting structure. If I take, let me take this wave vector. Again, I've told you we're not really dealing with wave vectors, we're dealing with director fields. But I'm going to take them on a loop around this point. So I'll take the loop to be this loop. Excuse me. This is an invariant. It doesn't matter which loop I take. So I take this like this, it'll come like this, over like this, switches like this, comes back pointing in the opposite direction. So it has turned through minus 180 degrees. Divide that by 360, and we would call these invariants minus a half. Okay, how about this one? Now take k here, okay, and I follow it around the loop, and it goes through plus 180, plus pi. Divide by 2 pi, I get him a half. Okay? So connected in two-dimensional patterns, the natural particles, as it were, are these point defects, and they have topological topological orders of a half and minus a half. So halves. So that you get automatically this Z2 symmetry. Okay? In other words, we started off with the problem just with translational and rotational symmetry. We didn't put in that there's going to be SU2, anything like that. Out comes from a phase transition, an instability, where we get this nipple forming, okay? We get these VX pairs formed, okay? And these concave and convex destinations have this property of this topological constant of invariant, the half. Okay. So now I look back on this, and what happens here, in reality here, is we don't get this solution here at all. What we get is between here, the focus, and the point at which this angle here, the angle of the K, is going to reach 43 degrees, we will indeed get a phase grain boundary in which there's this discontinuity, like the thin film blister. But then when this angle gets too much, okay, we get these nipples forming. So we get a whole set of nipples. So it's like not a line of dislocations, but a line of VX pairs. And this is actually what you see if you do the experiment. And you can more or less kind of say, to minimize the free energy, roughly where those should be put. Okay? So there's a very different outcome and problems where you actually have director fields from vector fields. Okay? The vector field, the thin blister, had this solution throughout over the whole shock. The director field solution actually, because you see, it doesn't cost the director field anything to do this. There's no cost in that. Okay? So director field solutions form these VX pairs naturally. Okay? So you have a natural formation of these particles, okay, with this Z2 symmetry. So now you might say, well, let's look at 3 dimensions. There's nothing two-dimensional. I mean, my original example of convection in a fluid heated from below, of course, it was a 2-dimensional example. And most patterns we look at, we tend to look at 2-dimensional patterns because they're easy to visualize and send light through the layer. But there's nothing to stop having 3-dimensional patterns. This whole theory goes through the very same way. Okay? Everything is the same. Okay? Everything is the same. So now, what are these guys going to be? Okay. Well, if you look at the point analogs in 3 dimensions, they actually have their homotopy is such that actually they're not robust. But what is robust is strings of these guys. In other words, put this guy here on a backbone. Okay? I'm going to put him on a backbone, and I'm going to make him... So I have this sort of concave destination. I put him on a backbone, and I bring it back like that. So I'm looking for periodic solutions in this direction. Actually, to get all the topology right, you can treat here B as 1, and then this is Laplace's equation. So, for instance, you're looking for these concave destinations are the solutions of Laplace's equation, where the complex solutions are just z to the half. Okay? Z to the half. These ones are z to the minus a half. Put these two of these together, z minus a to the half, z plus a to the half, and let the a go to 0, and you get z, and that's a saddle. Okay? So, so these things are... So we have these destinations. Now we're going to put it on a backbone. And you can actually write down solutions, like for this equation, you know, the unregularized equation, and as long as you take account of any multivaluedness. And what you get. Now, here's the wonderful thing. Now, we'll put a backbone on this guy, too. Now, what are the possibilities? With the x, I can bring him back exactly without twisting him at all. Okay? So that's 0. Okay? But I can also give him one full twist, bringing him all the way around. Okay? So this guy has a and you can show this as a topological invariant as well. So this is one topological invariant, and the other is 1. Okay? Plus or minus 1. Okay? So you can twist that. It's like a dislocation or a vortex. Okay? You go around once. Okay? You can get a twist. Actually, if you have a dislocation and you make a three-dimensional string out of it, okay, you get these things called scroll waves. Scroll waves is what gives you this fibrillation phenomenon in the heart. What I'm looking at is, in fact, the analog of these scroll waves in the heart, but with the backbone not of dislocations or vortices, but rather with these disclinations. Okay? So, but how about this guy? This guy. When did I start? Okay, that's perfect. So, what happens with the concave destination? Well, I can bring him back in several ways. I can bring him back with no twist, but I can also bring him back with full twist, but I can also bring him back with a third twist. Right? I can tie this guy, when I bring him back around the backbone, I can put this sector onto this sector, okay? Or I can twist the other way. So now I get all the topological invariance, plus or minus 2/3, plus or minus 1. Okay? Absolutely naturally. I didn't put it in. This is an instability, a phase transition that happened in this system which originally had translational and rotational invariance. That was the symmetries. It was stressed. The stress causes a pattern. The patterns come together in patches. The patches form these defects, these point defects, and these point defects have these wonderful properties. So this V string, I think I might call it a quark, because it has spin and charge. Okay? Also, its energy is proportional to the length of this phase grain boundary, is like L. This guy, on the other hand, he spin half, but now his sort of other invariant is 1. Okay? So we'll call these guys leptons, plus or minus 1. I mean, they're not really leptons, and these aren't really quarks, but they have some similar properties. Also, these guys, the amount of energy for this curve is much less than the energy for this guy. So roughly it goes like the log of the size. So the effective mass of these leptons is much less than the mass of these quarks. So now this is a game we can play. and which I haven't been able to calculate yet. I have trying to work out what I'd like to show is in a VX formation like this, where I can make a hydrogen atom, because I'll put him on a small loop, and I'll put him on a huge big loop around like that. Okay, so this is nucleus size, this is atomic size, and if I choose 3 of these together to give a +1 or +1 charge, then I would have sort of like a hydrogen atom. Okay, but what I'd like to do is somehow look at the free energy of this guy alone, the free energy of this guy alone, and show that the interaction free energy goes like 1 over the distance between them. Because that would suggest that there may be, in the far field, the force laws would be kind of what we expect. The force laws between the quarks, of course, are much more complicated. But anyway, so that's the. So I got a sort of kick out of this that without, you see, I went along to my friends who do standard theory and all this sort of thing, and you know, there's a big hullabaloo about. They write down just a Lagrangian, essentially. It's like me writing down a free energy with various symmetry properties. I mean, what I would probably like to do is put down think of these as wave patterns and sort of have a Lorentz invariance in the background, but that's details. What they do is they have to put in all the Z2 and the SU2 and the Z3 and the SU3. It's actually put in by hand. Okay? That's not really a theory. Why do these particles emerge in the first place? Well, they say because we see them there, and therefore we put them in this Lagrangian, and lo and behold, we choose constants, right? We get to predict behavior which seems to be consistent with what's found. The nice thing here is that these particles emerge, these V strings and X strings, emerge naturally as phase transitions, as instabilities from a background which is has just some very, very overall, very simple symmetries, okay? But it's stressed, okay? So, I mean, we can play also games like, what is the fundamental wavelength that I'm talking about here? Is that the Planck scale? Is that, and so on like that? What's the nuclear scale? What's the atomic scale? And so on. So it's kind of a bit crazy, but at my age, I can do crazy things. Thank you.
So initially I wanted to have David Lenny at this conference, and I would love to know what